Gravity is a familiar force. It keeps our feet on the ground. It governs the motion of planets. But gravity presents a challenge for physicists. The other fundamental forces of nature are described by quantum field theory. Quantum field theory describes forces as exchanges of particles. For example, electromagnetism is carried by photons. Gravity, however, resists this description. Attempts to quantize gravity using traditional methods have encountered serious difficulties. These difficulties arise from the nature of gravity and its relationship to space and time. String theory offers a different perspective on the universe. String theory proposes that the fundamental building blocks of nature are not point-like particles, but tiny vibrating strings. These strings are incredibly small, far smaller than anything we can currently observe. Just as different vibrations of a violin string produce different musical notes, different vibrations of these fundamental strings give rise to different particles and forces. This elegant framework has the potential to unify all the fundamental forces of nature, including gravity, into a single coherent theory. This unification is a major goal of modern theoretical physics. Imagine a guitar string vibrating. The different ways it vibrates produce different notes. String theory proposes a similar concept for the universe. In string theory, the universe is not made of point-like particles. Instead, it is made of tiny vibrating strings. These strings are much smaller than anything we can currently see. Each vibration of a string represents a different particle or force. Just like different notes on a guitar, different vibrations create different particles. This means that everything in the universe, from the smallest particles to the largest stars, is made up of these vibrating strings. One of the vibrational patterns of these strings corresponds to the graviton. The graviton is the hypothetical particle that carries the force of gravity. In string theory, the graviton emerges naturally from the vibrations of closed strings. This is a significant achievement because it provides a consistent framework for incorporating gravity into a quantum theory. The graviton is thought to be massless and to travel at the speed of light. It interacts with matter and energy, mediating the force of gravity. Section 5. Closed strings, the fabric of space-time. Unlike other force-carrying particles, which are open strings, the graviton is a closed string. This distinction has profound implications for our understanding of gravity. Closed strings, unlike open strings, are not bound to any particular brane. Branes are higher dimensional objects that exist in string theory. The fact that gravitons are closed strings suggests that they can propagate through all dimensions of space-time, including any extra dimensions that might exist. Section 6. Unveiling hidden dimensions. String theory suggests that our universe may have more than the 3 spatial dimensions that we experience. These extra dimensions are curled up and hidden from our view. The existence of extra dimensions is a radical concept, but it arises naturally from the mathematics of string theory. The presence of extra dimensions could have profound implications for our understanding of gravity. One possibility is that gravity, as a closed string, can leak into these extra dimensions. This could explain why gravity is so much weaker than the other fundamental forces. Section 7. The weakness of gravity, a cosmic mystery. Gravity is incredibly weak compared to the other fundamental forces. Consider a simple experiment: picking up a paperclip with a magnet. The tiny magnet easily overcomes the gravitational pull of the entire Earth on the paperclip. This demonstrates the vast difference in strength between electromagnetism and gravity. This weakness of gravity is one of the biggest mysteries in physics. Why is gravity so much weaker than the other forces? Section 8. String theory's explanation: gravity's leakage. String theory proposes that our universe has more than the 3 spatial dimensions we can see. These extra dimensions are curled up and hidden, too small for us to detect directly. Gravity, as a closed string, is not confined to our 3 dimensions. It can leak into these hidden dimensions, spreading its force over a larger volume. This spreading out would dilute gravity's strength in our 3-dimensional world, making it appear much weaker than the other forces. Section 9. Experimental validation, the ultimate test. String theory's explanations for gravity and extra dimensions are compelling. However, these ideas remain theoretical. Currently, we lack the experimental tools to probe the incredibly small scales where string theory's effects would be noticeable. Developing such tools is a major challenge for physicists. Finding evidence of extra dimensions or observing the graviton would be groundbreaking. It would provide strong support for string theory and revolutionize our understanding of the universe. Scientists are actively pursuing various experimental avenues to test these predictions and search for evidence of string theory. Section 10. Conclusion. A new perspective on gravity. String theory offers a radical and elegant perspective on gravity. It suggests that gravity is not just a force, but a manifestation of the vibrations of closed strings. The concepts of gravitons, closed strings, and extra dimensions provide a framework for understanding gravity's weakness and its place in a unified theory of physics. While experimental validation remains a challenge, the theoretical beauty and potential explanatory power of string theory continue to drive research in this exciting field.